Today I'm going to talk about covalent bond energies, which we talked about a little bit in the last chapter with thermodynamics, and also metallic bonding. So first, just to define bond energy. So the bond energy is the energy required to break 1 mole of the bond if it's in the gas phase. And some of these are listed here. So as the strength gets as the bond strength goes up, the energy that it takes to break that bond is going to go up. All right. And then bond length is another topic that relates to this. And the bond length is the average length of a bond between two particular atoms in a large number of compounds. So a carbon-carbon bond length with a single bond would be they've measured the distance between two carbon atoms in many different molecules and then averaged them to give you the bond length that's there. And what you can see from this table here is that as the bond length, as the bond order increases, so as we go from single to double to triple, the bond length goes down, so the atoms get closer together, and the bond strength goes up. So a triple bond is going to require more energy to break than a single bond, which I think should be intuitive. All right, and then in addition to that, you can see that, or we've talked about in the past, that bond breaking always requires energy, which means that it's an endothermic process, and bond making, or forming bonds, is a process that releases energy, so it's going to be an exothermic process. Right, we can find the delta H for a reaction by comparing the bond energies for the reactants versus the products using this equation here. So the delta H of reaction is going to equal the sum of the bond energies of the bonds broken minus the sum of the bond energies of the bonds formed. Okay, and the ones that are broken are usually the reactants, and the ones that are formed are usually the products. And so this is the opposite of what we've been doing in the past in terms of where products and reactants are. So just keep that in mind. All right, so now let's do some practice problems using that equation. So we have two problems here. Calculate the delta H of reaction for the following reactions using the bond enthalpies provided above. And so in order to do this, we first have to know what the structures are so that we can tell what bonds are broken and formed. So first, let's draw the Lewis structure for each of these compounds. So for CH4, carbon is going to go in the middle, and then we have 4 hydrogens around it. Okay, and then for Cl2, it's just going to be Cl and Cl, and there'll be valence electrons around, or non-bonding electrons. And then that's going to become carbon with 3 hydrogens and a chlorine, and an H and a Cl. All right, and we just reviewed doing Lewis structures, so I'm not going to go through how to do all of these, but if you have difficulty drawing any of these, please come see me and I can help you figure out how to do them. Okay, so in the methane, this first molecule we have here, we have 4 carbon-hydrogen bonds. So for each little line between two atoms, you need to have a bond energy associated with that. So we'll have 4 times the bond energy of the carbon-hydrogen bond plus 1 Cl-Cl bond. Okay, and then we're going to subtract from that the energy of 3 CH bonds over here, and 1 carbon-chlorine bond, and then 1 hydrogen-chlorine bond, right? So that's going to equal 4 times 414, and I got this from the table that's in your notes, but it's also in your book on page 410, right? Plus 243, which is the bond energy for chlorine-chlorine bond. And then we're going to subtract the bond energies of those that were formed, because those are going to release energy. So it'll be 3 times 414 plus 339 plus 431. And if we add all of those up and subtract, we get negative 113 kilojoules per mole. So what we just did here was use bond energies or bond enthalpies to tell us how much energy is transferred in this reaction. And it turns out that this is an exothermic reaction because delta H is negative, and 113 kilojoules of heat is released when this reaction occurs. Now we're going to do the same thing here with this reaction. So here we have two carbons with 4 hydrogens. So we'll put 2 on each. And then we're also, if you were to add up the electrons, you have 2 extras, and so those make a double bond between the 2 carbons. Okay, we also have H2, it's just an HH bond. All right, and then that becomes methane, which is 2 carbons and 6 hydrogens. And that is going to use up all the electrons that we have from those elements. Okay, so to do this problem, now again, we're going to add up the energy from the bonds broken minus the energy of the bonds formed. So it'll be the carbon-carbon double bond plus 4 times the carbon-hydrogen bond plus the hydrogen-hydrogen bond minus 1 carbon-carbon single bond over here and 6 carbon-hydrogen single bonds. Okay, so that's going to equal 611 plus 4 times 414 plus 436 minus 347 plus 6 times 414. All right, and we add all those up, we get negative 128 kilojoules per mole. So again, this is another exothermic reaction, and we have a little bit more heat released in this one than we did in the previous one. All right, now the final thing that I want to talk about is metallic bonding. And we're not going to spend a lot of time on this, but it is an important thing for you to know. So in a metal, we have what is sometimes referred to as a sea of electrons. So that's when metal atoms bond together and make a solid. Each metal atom donates 1 or more electrons to this sea. And so the electrons just move freely among the positively charged nuclei that are in that solid metal. Okay, and this contributes to the properties of metals. So the first one is malleability, which is the capacity that metals have to be pounded into sheets. So that's something you can do with a metal that you can't do with other solids, for example. All right, and then ductility is their capacity to be drawn into wires, which we also know can be done with metal, and that's why it's so useful to be able to use metals in wiring and things like that, because they also conduct electricity, and turns out they also conduct heat. And that is because of their sea of electrons. So the electrons are very loosely held. You hopefully remember that things on the left side of the periodic table have lower ionization energies than things on the right side, so they don't hold their electrons as tightly. And that's because for the number of shells they have, they don't actually have that many protons in the nucleus. So the electrons can move around really easily, and that is what gives us the ability to conduct electricity. All right, so we'll discuss this a little bit more in class and do some activities, but that's the extent to which we're going to discuss metallic bonding.